Okay, we are ready to do worksheet 3D for the Math 4 course. So we're dealing with the half-life of radium that is 1600 years. We're starting with a 20 milligram sample. So the first thing that we're going to need to do is to come over to the side and figure out what R is. 1600 goes underneath that. So by the time that we divide natural log of 2 divided by 1600, all right, that is going to give me 4.33 e negative 4, which means that I'm going to have 3 zeros and the 4, and we'll probably go ahead and do that. All right, so we're going to use that in our formula. So our formula was that we would take the original mass, or well, we're writing a function right now. So I'm trying to remember what it was. Oh yeah, MT equals the 20 milligram mass times E to the negative T. So that's what our function should look like that we're going to be using. Then we ask the question, how much will be there after 4,000 years? And of course, all of this is dealing with years. By the time I punch that into the calculator, of course, remember the decimal and the 4,000 probably need to stay inside the parentheses of your E. Negative 0.000433 times 4,000. And that E is going to give me 0.1769. And then I'm going to multiply it times 20. And that's going to give me 3.53. I'm going to say about 3.5 milligrams is going to be left after 4,000 years. How you think about it, after 1,600 years, it'll be 10 milligrams. At the end of 3,200 years, it'll be 5 milligrams. So, by the end of 4,000, it being less than 5, that's the reasonable answer. Now we're going to work it the other way. We're going to say, what if there's only 16 left out of the 20? And the time is the unknown. So we're going to first of all divide both sides by 20, which that is 4/5 or 0.8. I'm going to move my 0.8 over here because I'm going to write this as a log base E of 0.8, and my exponent goes all the way over here. And so now I need to know what is the natural log of 0.8. Okay. So the natural log of 0.8 is negative 0.223. And when I divide that by the decimal that I've got over there on the right, 0.000433, I get 515.3. So it's about 515. So that would be 515 years. Of course, if it cut, we're talking about half-life. After 1600 years, it would be 10 milligrams, but we're only going down to 16. So it makes sense that it's much less than the 1600 years of a half-life. Okay. All right. Now, how much of the sample will remain after 60 days? And they do say T days. So T is in days. So we would say M of 60 equals 32 e to the negative 0.0277 times 60. So I'm going to say e raised to the negative 0.0277 times 60, close the parenthesis. I get 0.18975. Oh, and then I got to multiply it by 32 up front. That gives me 6.07. It's about 6 grams. Now the interesting question here is, what's the half-life? They've given us the constant that R is, and so the next question is, all right, and how long will only 8 milligrams remain? So we're going to put 8 over here and 32 over there, and e to the negative 0.0277 t. If I divide both sides by 32, then I've got basically 0.25 over here equals e to the negative 0.0277 t, which I'm going to want to rewrite that as an exponential, or excuse me, as a logarithm, log base e. Exponent goes over here, and my 0.25 goes there. You could also list it as 1/4 if you wanted to, which is really the natural log of that. All right, so we're going to figure out what is the natural log of 0.25, which is negative 1.386. And then I'm going to divide that by the negative decimal on the right, negative 0.0277. And that is going to give me a little over 50. So those were in terms of days. So this is going to be 50 days that 8 grams would remain. Now, we have to figure out what is the half-life. Well, we knew that the formula originally looked like this. And so we know what R is. Now remember, the original formula had a negative in the formula. So R itself is not negative. Now, that basically means we're going to multiply both sides by H. And then we're going to divide both sides by that 0.0277. And that should tell us what our half-life is. 0.0277 0.0277. There we go. 25.02. So its half-life is going to be about 25 days. I'm assuming that that 0.02 came from some level of rounding error. Okay. Now, after 3 days, a sample of radon has decayed to 58% of the original amount. Well, what we can do is we can, they want to know what is the half-life of radon. Let's plug in what we know. And we're going to have to figure out what R is in order to be able to figure out what the half-life is. So after 3 days, whatever the original mass was is decayed to 58% of it. Well, let's say we have 100 pounds of the stuff. Then at the end of it, we would actually have 58 pounds, right? So that should give us something to be able to solve for R, and then we can come over to the right and reverse engineer R. All right, so if that's, we're going to divide both sides by 100, which means we're going to have 0.58 equals E to the negative 3R. And then I'm going to rewrite that as a logarithm, base E, 0.58, and my exponent negative 3R goes over here. That would be asking what is the natural log of 58, and then dividing by negative 3. All right, so natural log of 0.58 is negative 0.5447. And when I divide by negative 3, I get 0.1815, and some change. Now, I'm going to leave that 1815 decimal in my calculator because we also had figured that if R equals natural log over H, there is something that I have taught my students in years past, and that is what I call switcheroo. I'm going to go back here and go to this one, and notice that when we started with this and H was on the bottom and R was on the left, by the time we finished with it, H was on the left and R was on the bottom. They switched places. These two steps of algebra is what I like to call switcheroo. And so we actually can switch this out like that. And so now we're talking about natural log of 2 over 0.1815 and so on. And so I'm going to call up on this calculator natural log of 2, close the parenthesis, divided by second answer. And that'll bring up my last decimal. And that gives me H is about equal to 3.8. So that would be about, and they were talking about in terms of days. So if it decays after 3 days to 58%, it's going to decay to 50% at the end of 3.8 days. There's a little bit of change to that, but that's about as close as we want to get. Okay. All right, now we are at problem number 7, and we have 6 more. I think I'm going to pause here and cut this in half.